let's look at the opposite in some respects to charging a capacitor, and that's discharging a capacitor. So here I'm going to have I've done something, somehow I've charged up this capacitor, and at time t equal to 0, it's fully charged with plus Q naught and minus Q naught on the two plates. And I'll put it so that it will cause a current to flow through the resistor. And I know that when I close the switch, and again I'll set it up so that I close the switch at time t equal to 0. When I close the switch, then this positive charge is going to move around to neutralize the negative charge on this plate. So one expects the current flow to really be in this direction, positive current flow. But it turns out that these problems are always easier to do and to think about if I choose my sign convention in such a way that I think about this when I was charging this capacitor, I would have had current flowing in this direction into the positive plate. And so I will always choose current flow so that it's going into what I want to be the positive plate here. Now, in the course of things, what we should find is, once we solve for I, we should find that this becomes a negative value, and of course it will. So again, as this current flows through, I'll get a time-varying charge on the two plates. So now it becomes little q and minus q. I start again at this at the switch, and start on one side or the other. This way I go. I went around this direction, in the same direction as what I'm calling the direction of positive current flow. So I go across the resistor, and current's flowing in this direction, so it always goes from high to low, so the last sign it hits negative. And then I go across the capacitor, and that's going to be Q over C, the charge on the capacitor divided by its capacitance. And the last sign I hit as I come across it is the minus. And again, I know that I is dq dt, and so I go ahead and plug that in for I. So I get a minus R times I dq dt. And over here I'll get a minus Q divided by C. And again, we get a differential equation. Here I've rearranged it a little bit. I've just solved for dq dt, so take this over to the other side and divide through by R. And when I take it, it becomes positive. Multiply through by minus R, I get a minus Q over RC. And I could write that as the time constant again, if you like. But again, I've got this differential equation that relates this function of time, Q of t, that I want to its derivative. Again, this is a little easier to solve maybe than even the first one. In this case, I simply divide both sides by 1 over Q, so this becomes 1 over RC, 1 over the time constant. So this right-hand side is a time constant. 1 over the time constant, negative. And I just note that the total time derivative of the natural log of a function of time q, well, I take the derivative of the natural log, I get 1 over q times the derivative of its argument, which is dq dt. Use the chain rule to go from here to here. So I actually go this direction, but once you get here, then you can verify it in that form. So I get the total time derivative of the natural log of q is equal to this constant over here. And that's an easy one to integrate. So I do an indefinite integration on this side and this side. Indefinite integral of this derivative of log q is just natural log of q. And the indefinite integral of a constant is just t times that constant. And then I have to put in an integration constant again. And this time I won't put it in as a, but I'll certainly if a is a constant, then natural log of a is also a constant. So here's my integration constant in a convenient form for this problem. And now then I can raise both sides, e to the natural log of q, and this has got to be the same thing as e raised to this power since the two powers are equal. The e to the natural log, they're inverse functions, so this side just becomes q of t. The sum can be written as a product. That's just using, again, the properties of exponentials, e to the minus t over rc, times, since it's a plus here, this simply becomes time, e to the log a. And that shows you why I chose it in that form, because again, these natural log and the exponent are just inverse functions, and so this term just reduces to a. And so I get a particularly simple solution. Q of t is a e to the minus t over rc. And now then I can determine that integration constant a, as it turns out now, from our initial conditions, because I know that at time t equals 0, the charge on the capacitor plates was q naught. And so plug in q naught on this side when t is 0, t 0 here, but e to the 0 is just 1, and so I find that a is just q naught. And so we get the solution for the charge on the plates as a function of time. It starts off at its maximum value and then falls off exponentially, this factor. Once I have that, then I can get the current flow, because the current is just I is equal to dq dt. And if I differentiate q of t, I get minus q naught r over c, e to the minus t over rc. And again, now you see, in fact, that I do get the physical flow of the current is in the opposite direction that I assigned as positive current flow. So that negative sign says, yeah, it really does go in this direction. It goes in the opposite direction, which is what we could intuit from its original setup. We can identify this RC as the time constant, and so I get Q naught, the initial total charge on the capacitor, divided by the time constant. And if you look at that, that's got the right units for current. It's coulombs divided by seconds, which is just amperes. Again, it's often convenient to plot these, and for the charge on the capacitor, it starts off at Q naught and falls off exponentially. So that's just exponential decay. The current in this fashion is really negative, but most of the time people plot the absolute value of the current, and that's what I've got plotted here, not the current itself. It would have been negative. But just calculate the magnitude of the current, and that's just this expression. Take the absolute value, that gets rid of the minus sign. And it starts off at a maximum value of Q naught over tau, and it likewise falls off exponentially. So to kind of summarize, we've got the following sets of equations. For discharging a capacitor, we get this for the charge on the plates. It starts off at Q naught and decays exponentially. And the current starts off at its maximum absolute value when t is 0, and it falls off exponentially as well. In the above expressions, we use the time constant. I naught, sometimes you'll see that as just the Q naught over tau. A lot of people just lump it as I naught. If you look at the voltage across the capacitor, it's just at time t equals 0, it's just I naught times R, and that's the same as Q naught over C. And so sometimes you see the voltage written, and this is the voltage drop across the resistor is this minus E naught over R. Well, that's the discharge equations for the capacitor. Again, we'll work an example here, but I would say pay close attention to the reading assignment in the book, and be sure to look at the examples there particularly carefully.